We recorded our data yesterday. The mass of the red cart was going to be more than the mass of the blue cart because we put a mass on top of it. But we do have a mass of the blue cart. We titled our table. We have 10 pieces of data, or in some cases, we reduced it to maybe 8 pieces of data because of a couple of little issues. I can't remember if that was anybody in this class or not. Don't panic if that was the case. We can take 8 pieces of data or whatever if I told you that was okay. And then we got a plot graph. Today we're going to talk about the analysis with the graph and how to determine if momentum was conserved. If you remember, the problem was, is momentum conserved in a one-dimensional collision? So we haven't established that yet, right? We've collected data, but we haven't done anything to show that momentum is or is not conserved in a one-dimensional collision. Hey, what do we do typically when we have a data table? We plot a graph. Yeah, we plot a graph. So we've got initial velocity in the first column here. We've got final velocity in the second column. We're going to plot a graph of final velocity versus initial velocity. Now, you guys know with that practice lab that you did, the title of the graph is always y-axis versus x-axis. Y-axis versus x-axis. So in this case, it would be final velocity versus initial velocity, or final velocity as a function of velocity, or something like that, as long as final velocity is mentioned first. Now, what else is required for the title? Something that Google Sheets will not automatically do. We want to put our initials after that. Just put your initials after the title in brackets, just so that I know you didn't copy and paste somebody else's graph. Not that you would do that, but just to ensure that that hasn't happened. All right, now we plot our graph, final velocity versus initial velocity. Don't forget your units. I haven't put units in here because I got no numbers here, right? But when you put your numbers in, you're going to have units in there. You're going to plot a scatter plot. Always a scatter plot in Physics 30. I'm not suggesting to you that there's no reason to plot a bar graph sometimes, or a pie chart sometimes in biology or in chemistry or whatever. Scatter plots are not the only valuable thing to do, but they are in physics. So you're always going to plot a scatter plot in physics. Don't plot anything else. That scatter plot is going to have a bunch of data points, something like this. And you're going to draw this trend line. And that trend line should be, in this case, a linear trend line. It should match your data, but if your data is reasonable here, then it should clearly be a linear trend line. Display that equation, and that equation, remember, is going to have the slope in it. It's in the form of y equals mx plus b. That first number that you see beside the x is the slope. Now, remember, there's a box that you can check right below that, right below where you display your equation, that says show r squared. Sometimes people click that box, show r squared, and they think that that number is the slope. That's not the slope. When you show the value of r squared, that's only telling you basically how close your data points are to the trend line. In other words, how good your data is. Sometimes there's some value in looking at that number to see how good the data is, but we're not going to actually use that number in any calculation. So you want to display the equation, and you want to use the slope of that equation. And then, what are we going to do with that slope? In Physics 20, we looked at a few graphs: position versus time, velocity versus time. You remember the velocity versus time graph? The slope of that graph was the acceleration. Remember that? How did you know that? How did you know in Physics 20 the slope of velocity versus time graph was the acceleration? Because we told you, because your Physics 20 teacher told you the slope of that graph was the acceleration. In Physics 30, we have got to figure out what the acceleration, what the slope of the graph means ourselves. Now, in your practice lab that you guys did, I walked you through that process, right? I'm going to walk you through that process again for this one. This one's a little harder, although the process will be the same. Going forward, I'm going to expect with each consecutive lab we do a little bit more of you in terms of figuring out what the slope represents yourself. By the end of the course, we have got to be able to ourselves figure out what the slope of the graph represents, because we will see a graphing question on our diploma exam where we have to use the slope. It may be a graph that we've seen before. If we're lucky, that happened last semester. We got lucky, and it was a graph that we had actually done in class, or it may be a brand new graph that you've never seen before. Shouldn't be stressful either way, because by the end of the course, we'll have the technique down pat to figure out what the slope of the graph represents. All right, so walk with me again through this to figure out what the slope represents. Remember the next step here? Once we've plotted a graph, once we've got our title, we've got our equation displayed, we've got our graph plotted beautifully. The next step is two columns. You remember what they are? What's the first column? Look like your hand was going up there. No? Okay, no, that's fair enough. I just called on you because I thought your hand was going up there. Yeah, we want to come up with an equation from the graph and an equation from class. Always. When you get that question on your exam, and you will get that question on your exam, maybe not this graph, might be this graph, we get lucky, but probably not. We will start off with these two columns, the graph and class. So we need to come up with an equation from the graph, we need to come up with an equation from class. The one from the graph is always easy. It should be ridiculously easy, because every straight line graph in the history of humankind has the same equation. What is it? Yes, you said, Nick, you said, Margaret, you said the equation is y equals mx plus b. Any straight line graph, and the one that you get on your exam, will be a straight line graph. So the equation will be y equals mx plus b. Now, we want to tailor this equation for the graph to this specific graph, right? So we're going to replace, I should say, y with whatever appears on the y-axis. What does appear on the y-axis? What variable appears on the y-axis? Yes, so we're going to say vf. When we're writing variables on the y-axis, we use words. But now, when we're coming up with the equation, we're going to use symbols, right? So vf. M stands for slope of the graph. Yep. We're going to use the word slope because we don't want to get it mixed up with mass, right? We always replace M with slope so that we don't mix up the slope with mass. And x-axis will be, what variable is on the x-axis? Initial velocity of cart 1. So we're going to say v1 initial. And then B stands for the y-intercept. And in most times, I'd probably say 75, 80% of the time we see a graph, the y-intercept will either be 0 or very close to 0. If the number for your y-intercept when you display your equation is small compared to the numbers on the y-axis, we can just kind of cross it off. Even if it's not quite 0, probably close enough to 0 that we can cross it off. So here's the equation that demonstrates this graph. Vf is equal to the slope times v1i. That makes some sense, right? There's a linear relationship between Vf and Vi. We can see that by the straight line graph. Now we have to come up with an equation from class. Oftentimes, it's directly from our data sheet, but not always. Right? When we did our practice lab, it was directly from our data sheet. Remember, F times delta T equals M times delta D. This time, it's not directly from our data sheet, but it is one that we've done in class. What equation that we've used in class has, in the context of a collision, because that's what this is, right, has both Vf and Vi. What equation in the context of a collision has both Vf and Vi? We're not going to find it directly on our data sheet, although it ultimately comes from our data sheet. Yep, Pi equals Pf. Now, that doesn't, we don't see Vf and V1i in there, but we can turn it into that, right, Margaret? We can make it into V and V, right, if we just do something with this. We're going to say M1 V1i, because remember yesterday the red cart was moving with a certain initial momentum, plus 0, because the blue cart was at rest, equals, they stuck together, so we would say mass total times Vf. Now remember what we do next? We want to make this look like the equation from the graph. In other words, since we solved for VF in the graph equation, we want to solve for VF in the class equation as well. So let's take the MT over by dividing. VF is equal to mass 1 over mass total times V1I. Is this process seeming a little familiar to you here? I'm not asking you, could you have done this yourself? Maybe some of you could, maybe some of you couldn't. That's okay. We're not at that point yet where I expect you to be able to completely do this process by yourself. I just want it to look a little familiar to you. I want it to make sense to you, and I want it to be like, oh yeah, I kind of remember that. That kind of makes some sense from what I did the other day in my practice lab. Anybody remember what I do next? Good. Yeah, cross off the values that are the same in both. So VF is in both. Let's get rid of that. Like some people say we cancel. Technically, we're not canceling because canceling is one equation from two different sides. But if you want to say that, whatever. Like it's not technically the correct mathematical term, but in the end, like as long as you're doing the right thing, it doesn't really matter. We're also going to cross off, by the way, V1I because it's in both. Ronnie, what am I left with on the left side? Slope. What am I left with on the right side, Ryan? And 1 over mass total, right? So we're going to say slope is equal to mass 1 over mass total. Who would have even thought? Who would have predicted, without doing an analysis, that the slope of this graph represented the ratio of the first mass over the total mass? Who would have predicted? Not me. I wouldn't have predicted that. But through an analysis that is the same, fundamentally the same, every time we do it, we were able to figure out that the slope is equal to mass 1 over mass total. Now, what does this tell us in terms of the context of the lab that we did yesterday, where we're trying to verify the law of conservation of momentum? We've got the slope, right? The slope comes from the graph. Do we have mass 1? Yes, that's the first thing that we recorded, right? Mass total, well, we can find mass total by adding the red mass plus the blue mass, right? So we've got this too. Here's the thing. Theoretically, we know by this graphical analysis that these two should be the same, right? If they are the same, so you're going to determine the slope, right, from Google Sheets. You're going to calculate mass 1 over mass total. They should be the same. If they are the same, then we've just verified the law of conservation of momentum. Now, that's a little bit of a leap here. How can we say that? If those two numbers are the same, we've verified the law of conservation of momentum. How can we say that? If they're not the same, we've disproven the law of conservation of momentum. How can we say that by showing these two are equal, theoretically they should be equal, by showing that they are equal, we have shown that momentum is conserved in a one-dimensional collision? We made an assumption earlier on here. We assumed that PI equals PF. Margot said that, I think, right? But wait, we were trying to prove that PI equals PF, yet we assumed that it was correct. Here's the thing. If we assumed PI equals PF, and with that assumption, the slope should equal mass 1 over mass total, and the slope does equal mass 1 over mass total, what does that tell us about our assumption? It tells us that our assumption was correct, right? So we're assuming it to be true, and then we're essentially checking to see if our assumption was correct. So if these two numbers are equal, then we've shown that momentum is conserved. If these two numbers are not equal, then we've shown that momentum is not conserved. Now, realistically, are they going to be exactly equal to each other? Probably not, right? Like, it never works out that perfectly. If it does, that's great. It's possible. Like, theoretically, it should, but it won't. Like there's always outside factors that mess things up a little bit. So what we're going to do is do a little percent difference calculation to see if we're close enough. Some of you have probably done percent difference calculations in chemistry class. Percent difference, we're going to say actual minus theoretical. Sometimes you see a slightly different form of this, but it boils down to the same thing. The actual value minus the theoretical value over the theoretical value. And then we take the absolute value of that so that we always get a positive number. So if the actual value is less than the theoretical value, we get a negative number, right? Take the absolute value so it's always positive. Times that by 100. Now, the theoretical value, theoretically, we should end up getting whatever, theoretically, the value is mass 1 over mass total. Before we even did the experiment, we could have divided those two numbers, right? So theoretically, that's what we should end up with. But what do we actually end up with? The slope of the graph. So you're going to say the slope minus the ratio of the masses divided by the ratio of the masses times 100. And our cutoff is going to be, we're going to say 10% here. If the percent difference is less than 10%, then we're going to say, yeah, momentum was conserved. And if it's bigger than 10%, we're going to say, no, momentum wasn't conserved. If you get 12% error, like the correct conclusion is momentum was not conserved. And as long as you've done everything right, then that's still going to be full marks. You're not going to lose marks because you proved momentum was not conserved here. Okay, as long as you've done everything right throughout the lab to get that 12%. If you get 12% and you made a mistake somewhere, that's a different story, right? But on the same token, if you get 6% and you say momentum was not conserved, or if you get 12% and say momentum is conserved, well, that's when you're going to lose marks because your conclusion doesn't match your analysis. Does that make sense? Science is about that. Well, it's actually about disproving stuff, not about proving stuff, right? So I'm okay if you get 12% or 15%, as long as you conclude the right thing, the thing that's consistent with it.